My name is Tim Murray. I'm from the Android performance team. And I'm going to talk about Systrace, which we already talked about a bit earlier with the system tracing in Android Studio. But I'm going to talk more about the old style of looking at traces, as well as what you actually do with a trace. So what are the big performance goals for a game? There are really two big ones. Number one, you need to get the gameplay fast. If the user has to wait 10, 20, 30 seconds to launch a game, then they're gonna quit. They're not gonna be happy with your game. They're gonna find another game. The other thing is you need to maintain interactivity during gameplay. It's great if you get to the gameplay fast, but if the gameplay is super janky, dropping frames all over the place, it's really bad. So the problem is mobile devices are really complicated. You look at a current flagship phone, and it's an 8-core CPU with heterogeneous CPU cores. And there's a giant GPU, and your flash performance is totally different than what you would expect on a PC. There's a lot going on. You really can't assume anything about how your code runs. I've been looking at performance for years now. I can't predict how code will run. No one should assume how their code runs. So that's why we have Systrace. It shows you what actually is running. It is sort of truth, like capital T truth. If Systrace says something ran at a certain time, it ran at a certain time. You cannot lie to it. You cannot trick it. It's outputting events from the kernel directly. Whatever Systrace says is happening is actually happening, which makes it really great. The other great thing about it, because it's so low level, the overhead is basically zero. We will just turn on Systrace and let it stream into a buffer, like an in-memory buffer. So you record, you can get the last 10 or 20 seconds out of it. It has no measurable overhead. It's sub 1%. So we do that, and we find a ton of performance bugs that way. It's great. So first of all, let's talk about how to take a trace. And I'm going to not talk about the Android Studio side of things, because we already talked about that. I'm going to talk about the two other ways we have to take a trace. So first of all, most of the tools for tracing other than Android Studio exist in this open source project called Catapult. It's maintained by people from the Android team and the Chrome team, and it lives on GitHub. So you grab the Git repo for Catapult, and you end up with a Systrace Python binary in that directory, catapult systrace bin systrace. And that's kind of the main shell to using Systrace. If you want to take a trace from the command line, essentially you run that, and you pass a bunch of, they're called tags, to Systrace. And this will determine the kind of output you get in the trace. So here, it's going to take a trace containing scheduler information, so like exactly what the scheduler is doing at any given time. CPU frequency and CPU idle information, some Android Activity Manager and Window Manager information, then a bunch of information about the graphics stack, and then a bunch more things. Well, input is useful for game devs, but the other ones aren't too useful. Input shows you when an actual touch event happens, so that's really useful for game developers. The last three options are not tags. So -B is the buffer size. The buffer size determines how much you can actually record in a trace. So it's a per CPU ring buffer in memory. So here, this is in kilobytes. So on this device, I get 16 megs per CPU. Generally, 10 megs or so per CPU is totally fine on a high-end device. It kind of depends how much context switching you're doing, because that is probably what occupies the most space most of the time. You can get about, I would say it's about 1 meg, gets you about 2 seconds of a trace, so you could record a pretty long trace with this. Dash T is an optional argument. It tells you how long to record the trace for. If you don't pass dash T, you just press enter to stop the trace. And then dash O is where to write the trace. If you don't pass dash O, it defaults to trace.html, which is fine, but also very annoying when you start taking hundreds of traces, and they're all named trace.html. So here's the cool new thing in Android P, which is actually incredibly useful. So it's really annoying to have your phone plugged in to take a trace. And most of Systrace actually lives on the device. The Systrace binary is basically just talking to device-side stuff. So in Android P, we made it so you can take a trace from the device. The great thing about this is that you turn on developer options, and you get this quick settings tile. Once you turn it on, you can start taking a trace, and it will stream into that in-memory buffer. So you can turn on a trace. It has super low overhead, so you can just leave it on and do your thing and play your game, and then you see, like, hey, that seemed like it took a long time, or hey, I just dropped a bunch of frames. You pull down quick settings, stop the trace, and you've just captured exactly what the problem is, and you can just pull it off or email it to yourself and see what's going on. It will pop up a dialog that allows you to email it or share it to Drive or Dropbox or whatever. It's also saved to the device in data local traces if you do want to pull it off via ADB. The only special thing about the system tracing, like quick settings approach, is that they are compressed on the device. So you have to do some post-processing with Systrace and Catapult. And I think Android Studio is adding support for this soon, so you can import to Android Studio as well. But you process with the from file argument, and you will get a trace out of it, a normal HTML trace. So, OK, you got a trace. What do you do with a trace? Because it's kind of a lot. Let's go through a pretty simple one, and then we'll go through some gaming ones. So I don't know how legible this is. Systrace doesn't really present well. But essentially, you have a big timeline view here. So I took a trace of application startup, I think calculator startup. And at the top, there's some basic information about the overall state of the device, this interactions and alert stuff. The kernel line is where we can see what is actually running on every CPU core at any particular time. And then we start getting into a lot of per thread information below that we'll go into more detail about in a moment. So there's a lot more info than fits on the screen, so it does scroll up and down. So make sure you scroll. You also can navigate around the trace with WASD. So A and D to move left and right, and W and S to zoom in and out. You also have this palette, this floating palette that's at the upper right hand that contains 4 tools. The first tool is the pointer. The pointer lets you click stuff in the trace and see what it is. So here I clicked one of the calculator time slices, and I now get more information about that particular instance that it was running in the bottom half of the screen. So I can see here's its PID, here's the TID, here's the priority, here's how long it was actually running on the CPU. So you'll use the pointer a lot. The other thing you can do with the pointer is you can select a bunch of stuff. You can just draw a rectangle, and after you draw the rectangle, you get an aggregate view. So you can look and see like what was running during this time. And you can sort these and the normal stuff that you would expect. The fourth tool on here is called, I think, the ruler. But essentially, it allows you to mark a section of the trace, and you highlight it. And you can now scroll up and down the trace view, and that highlight will remain. So if you know, like, I've dropped a frame around here, I need to go look around the rest of the trace to see what's going on, You can highlight that and scroll up and down and know exactly where you are. The second and third things on the palette are a panning tool and a zooming tool, but they're equivalent to WASD. So you can use the palette tools if you want. You can use WASD if you want. It doesn't really matter. So if we scroll down, we can see per thread information, and we can see information about each thread's current state. So the first thing that you'll see, and it's hard to read, and I apologize. Do I have an arrow? I do have an arrow. So there's this stack of boxes. So essentially, the trace sections for a given thread are a stack. So you'll say, like, trace begin section, activity start, and then something else will say trace begin section, inflate, for inflated view. And so they appear as a stack in the trace. The other thing about that is at least as important for reading a trace is the kind of multicolored bar above each thread. And you can kind of see it. It's hard to see. But that tells you information about the state of the thread at any given time. Oh, you can see it in more detail there. So you can see there we've got a bunch of green sections, we've got some orange section, we've got some red, we've got some blue, and sections where it's just not colored. So yeah, there's some green. And if you actually click that green bar, it will tell you that it was running, and it will tell you how long it was running and which CPU it was running on. So you can track your thread's progress through the system that way. You can see, okay, it was running here for this time, and then it was blocked on something else, and then it woke up and figure out what's going on there. So the different colors are, there are 5 colors. Number 1 is green. It just means the thread is running. It's currently running on a CPU. You know it's actually making progress during that time. The only thing that could run when a thread is in the running state is an interrupt, and that lasts, sub-microsecond most of the time. So if your thread is running, it's actually on the CPU doing work. If it's runnable, that can mean one of 2 things. A thread will become runnable when it's been sleeping and something wakes it up. Or if your thread is just like, let's say you have a spin loop, just while one, do nothing. Eventually the scheduler will say, okay, you've exceeded the amount of CPU time you can have right now. I'm going to deschedule you and let something else run. Then your thread will be made runnable in that it could be running, there's nothing blocking it from running, but the scheduler has not selected it to run. The third state is sleeping. Sleeping just means there's no work for this thread to do, so it's not running. Usually it means you're blocked on, like if you expect that your thread should be running, but you see it's sleeping, it's probably actually blocked on a mutex somewhere because lock contention in user space does show up as sleeping. The last 2 are kinds of sleep inside the kernel. The orange is uninterruptible sleep in block I/O, which means you are waiting on disk. So if you see that a lot, it means you are loading a ton of data from disk, and maybe you shouldn't do that. The last one, red, is uninterruptible sleep. This means you are blocked somewhere else in the kernel. It's probably not I/O. It's probably related to memory management, because we do see that the vast majority of time in uninterruptible sleep is actually because of memory management. And so a kind of easy, quick thing that I do as the first part of reading any trace is you can select all of these bars above a thread and get an aggregate view. So here I can see that this particular thread was sleeping for 12 milliseconds. It was runnable for 0.6 milliseconds, running for 3.1. It looks totally normal, totally fine. But you can use this to get a sense of where your bottlenecks may be. If your thread is always running and you're still not meeting your performance targets, you're probably CPU bound. That's probably a good bet. If you see that your thread is sleeping and never running, maybe there's some lock contention, maybe you're waiting on GPU activity. It's not the bottleneck is not that the CPU for that thread. The bottleneck is somewhere else. If you're seeing a ton of block I/O, then you're probably reading too much from the disk at any given time, and the thread can't make progress because it's waiting for data from the disk. So that's kind of a good first check for where your bottlenecks may be. One other really helpful thing here, let's see, do I have an arrow? I do have an arrow. Up at the very top, this interactions and alerts area, it's really hard to read, but you can actually see when the user touched the screen, this input thing. So you can tell, like, when you have a trace and you know, I tapped the screen once and something happened and it was slow, this gives you a really good way to orient yourself in the trace. You can tell, okay, well, the bad behavior must be around here. So one of the most important things to do with a trace is to add your own trace sections. You can debug a lot of issues without having your own trace sections where you, as the app developer, know what your app is trying to do. But if you add your own trace sections, life gets so much easier. It's really 5 to 10 times faster to debug if you have your own trace sections. So from Java, you include this package. It's trace.begin section and trace.end section. The only thing you have to do is, because it is a stack, you need to actually make sure that every begin section has an end section. Or otherwise, Systrace, the trace gets really weird, and it's bad, and you won't like it. But of course, nobody in here really cares that much about Java, so for the NDK, you include Android trace.h, atrace begin section, atrace end section, and I believe that is supported on API 23 and up. So when you actually want to take an app trace, all you have to do is you take a trace, you add -a and your package name, and that will turn on app tracing for your app, and you will just get results. There is a trace section that I added to a random app at one point. And it just shows up as any other trace section. But it's really good for, when you're loading something or waiting on network activity, you know semantically what your app is attempting to do. You can express that information in a trace, and combined with everything the system thinks is going on, you can get a much better view of how your app performs. OK, so game traces. Because that's why we're here, let's look at a couple actual game traces. So just out of curiosity, how many people in here use Unity? OK, a pretty large number. What about Unreal? OK. And what about custom engines, not Unity or Unreal? OK, cool. So I took 2 traces each from 2 popular games, like current top 20 maybe. And I anonymized them to not kind of, put them on edge. And the first uses a custom engine. The second is a Unity game. So let's look at that first one. So this is app startup. And I don't have my notes, and that's really annoying. So this is what it looks like after I took the trace. I took it down a Pixel 2 XL running P. And so I open it up, and I can see this was launching a game. So at some point in here, I click the screen, and I think you can see that up at the very top, there's that one place where the second row in the interaction section is lit up, and that is where I actually touched the screen. So I started this game, and I wanted to see, is it fast? Is it good? And it took a few seconds. It wasn't too bad, but I thought it could probably be better. So here's the actual startup section for the game. And it looks a little weird because the UI thread it's called the UI thread in Catapult. It's actually just the main thread. It is the first thread, so that starts up first. That's where app code usually runs. The UI thread just kind of goes idle for a second in the middle there. Like actually, yeah, it's 1.4-ish seconds. It just doesn't run anything. It's asleep. It's not waiting on anything. I looked at other threads. Nothing else is running. That's weird. So, if you look at what else is running on the system, it's actually, like, it doesn't look, it might not look that idle. It's pretty idle. Like, there's some stuff running at the beginning of that time as probably, like, rendering the transition to, like, draw the window for the app. But by the end, like, nothing's running. App's just kind of waiting. So we can go and see what actually woke up the app. And here I've zoomed in to the very edge of that 1.4 second time, and there's a tiny little blue block at the end of that, where that main thread becomes runnable. And here I can see wake up from TID 0. And so wake up from TID tells you what thread made something runnable, which is really great because you can actually get into causation. You can say, this thread caused this other thing to happen, and you know it's real, it's true. But TID 0 means it's an interrupt. And that's really weird, because apps usually don't see interrupts directly. The only interrupt they ever really see is a timer interrupt. But let's just be careful and sure and scroll up and look. And yeah, during the, 20 or 30 milliseconds before, there's nothing really running. And we don't have interrupt latency of 20 or 30 milliseconds. That'd be wild. So I kind of wonder if the app is sleeping for 1.4 seconds. I think it's possible. This wouldn't show up on a profiler because you wouldn't see sleep in a profiler, but it really does look like the app is just sleeping during app startup. So let's go on to the next trace. So this is gameplay. And gameplay here has some load screens kind of in the middle. And I wondered what was happening during that time. The thing about gameplay and why I still use Catapult instead of Android Studio. Catapult will show you every process on the system, which is a ton of data, but it will also show you things like Surface Flinger. And Surface Flinger is great. And if you have no idea what I'm talking about when I say Surface Flinger, let's talk about how a frame actually makes it to the display on Android. So what is the basic life cycle of a frame? Number one, apps will render a frame. So your game will render a frame, and it will send a message to Surface Flinger saying, I have a frame ready for you to display. Surface Flinger will wake up every, at 60 hertz, I guess, and figure out which apps are visible. And it will build a list of all the frames to be combined into a form that the underlying hardware can deal with. So that list makes its way to a vendor driver and vendor hardware called the Hardware Composer. And it will take, maybe you have the status bar up or the home and back buttons, and all of that will get overlaid and turned into one frame buffer, and that final frame will be sent to the display. The great thing here is that Surface Flinger tracks every app and every frame. So if we look at Surface Flinger state, we can see exactly what is arriving when from any particular application. So let's go back and look at gameplay and look at Surface Flinger. So here we have this surface view row, and it's a counter. So the surface view is triple buffered, so you either have 0 frames pending or 1 or 2 frames. And you can see it's usually bouncing around, which means we are getting frames from the app. But again, there's a gap here. And it's about 700 milliseconds. And the game does do something with load screens. So let's go see what the app is doing, because this is probably a load screen. And here, yeah, we have this long 700 millisecond on draw frame section. And if we look and see what's actually happening, yeah, it's running for about, 190 milliseconds, and sleeping for 500 odd milliseconds. So it's waiting on other work to happen. Now there are these other two threads nearby that seem to be doing work. What's up with them? Well, they're running and sleeping and runnable for some of it. Let's see, is that, okay, yeah. So if you actually look at what these thread sections are, they're tagged with IOMX, which I know from other Android things is sound stuff. So I think what's actually happening here is the game is pausing its loading, or pausing, displaying frames in order to load more sounds. But you can see kind of before this big loading section, there's a lot of free CPU cycles. Like the game is not keeping the device that busy. This load screen could probably be fixed, like removed completely, just by moving a lot of this loading ahead of time to overlap with actual gameplay, because there's enough CPU time to do it. So that's the kind of stuff you can get out of Systrace in kind of less graphically intensive games. Now let's look at a really graphically intensive game. So this one uses Unity as well. And let's see, I think I have level start here, and then we have actual gameplay next. So for my level start trace, this is what I see when I first open it up. And you can see the surface view in the center there. And it does have a big chunk where Surface Flinger is not displaying anything because no frames are really arriving from the game. And if we actually trace from, highlight from where frames are being consistently delivered, in other words, before I started the level, to when they are being consistently delivered again, that's probably after the game is really displaying stuff, it's about 5.7 seconds. It's pretty long as a player to see that. So let's go see what the game is actually doing. So here is the Unity main thread. And the Unity main thread, if you look at Unity apps, you're going to be looking at the Unity main thread a whole lot. But you can see it is not super busy, which is weird and not great. So what is it actually doing? Well, it's running for, 3.1 seconds, and it's sleeping for 2.5 seconds. So what's actually happening during this sleep? So if we zoom in a lot, and now we're looking at a 300 millisecond period that I saw this 300 millisecond pattern repeat kind of consistently throughout this Unity main section. You see that it runs for a bit and then goes to sleep, and runs for a bit and goes to sleep, and repeat. And it looks really periodic. It looks like it's happening on frame boundaries. So let's see what's actually waking it up. So once again, we can zoom in, and there's a tiny little blue bar that is probably not visible from this. But we can see the wake up from TID 31526, which is something. So we can go scroll up to the top of the trace now and figure out what that is. Hey, it's the Unity choreographer thread. So what I think is happening here is that the game is running some Unity script. And in that Unity script, they're saying, they're trying to be nice and not block rendering, and saying, wait until next frame. But this is causing their load times to suffer a lot. There's probably a good 1.5, 2 seconds they could get back by not doing this during the actual load. Just because there is so much free time on that thread, and that is the bottleneck for the load here. There's actually very little I/O done here. One of the things we see in general on Android is that you're generally not I/O bound, especially on high-end devices. Low-end devices, like really low-end devices, are very different. But if you're talking mid or high-end in the past few years, flash performance has increased dramatically to the point that it's faster than a lot of desktop machines. And you're not that I/O bound most of the time. The biggest bottleneck is definitely the CPU, and that's what we see. Like even in this very graphically intensive game, it's bottlenecked by the CPU. Let's look at gameplay, because there's some interesting stuff there too. So once again, there's the surface view, and you can see it's kind of ticking back and forth in the middle there. And overall, it looks pretty good. Like I have very few complaints about this, but I can always be pretty nitpicky, so let's find something that is wrong. So it did drop a frame in the middle here. There is a place where it should have rendered a frame, and it just didn't. Like no frame was ready for Surface Flinger, so the app probably did not complete a frame on time. So let's scroll down and see what happened in the app to make it not complete a frame on time. So here is the Unity GFX device thread, which is actually dispatching the render calls. It looks like at one point it just skipped. So it just missed, like something missed a deadline somewhere, and it decided, hey, just drop the frame. We're not going to make it. So let's look at the Unity main thread and see what's going on. Aha, there is the kind of smoking gun. Immediately before that dropped frame from the Unity GFX device, we see a bunch of I/O on the Unity main thread. That's a little weird. I wonder why that happened. But then I scrolled up and realized that is exactly when I touched the screen to trigger some special thing in the game. So my guess is that I pressed a button in the game. There was something on the disk that was not loaded. And even though our disk throughput is really high, it's still disk latency. So it takes a while for, even if it was 20 bytes, it will still take a while to get those 20 bytes off of disk. That blocked the Unity main thread, which in turn caused the Unity GFX device thread to not render a frame, and that was seen as a frame drop. But overall, this is actually a pretty good game. It's running pretty close to a solid 30 FIPS, I think. But it is actually maintaining it and working really well. But there's always something you can improve with performance. You can always be harsher on yourself. But that's kind of the data we get out of Systrace. It's exactly what happened, and it allows you to tie it together across the system to figure out what actually went wrong. And coupled with the new support in Android P for triggering a trace on device, it's easier than ever to actually spot performance issues and figure out what's going on. So yeah, I guess questions.
You just mentioned that most of the games are not I/O bound, right?
Yeah.
So basically, it's true when the assets are uncompressed, but the APK is compressed itself. Of course, you can store some of the things without this deflate compression there. But in that case, the size is going to probably bypass the 100 megabyte limit.
Yeah.
So if you want to read 20 bytes from the disk, it's not like reading 20 bytes from the disk. You have to read a whole block of the zip compressed file, then decompress it, and then you have access to these 20 bytes. And that actually is something which you probably can't even solve with the higher speeds of the flash.
Sure, but with the flash, even the latency is still poor compared to, it's not like, spinning disk poor, but compared to something that's already in memory, it's dramatically higher. And you're always going to read some fixed amount, like I forget what the minimum granularity you can read from the flash is, but you're always going to read some block size from the flash. So it doesn't really matter if you have 4K to read or 3 bytes to read, you're going to read the same amount of data.
Yeah, there are multiple layers of caching everywhere.
Yeah.
So you have to invalidate all the caches, then read it from the flash, have it loaded into the cache of the flash, and then through all the file levels. Do you think it makes sense to store more assets uncompressed in order to reduce the whole overhead? So talking from the perspective is like on iOS, the assets are stored uncompressed on the device, right?
Mm-hmm.
And that could be one of the reasons why the loading performance or the performance when you're loading the next level or something like that is much higher because you don't have to uncompress stuff.
So I don't actually think that's the reason for the difference in like loading performance. It looks pretty much like the difference in single-threaded CPU performance. It matches pretty closely with the difference in single-threaded CPU performance. What we see, especially in Unity apps, is that Unity apps on 5.6 or something like that are still primarily single-threaded, especially around load times. And they're CPU-bound on Android. I bet they're still probably CPU-bound a lot of the time on iOS. iOS generally has higher single-threaded CPU performance, so load times are better. So more multi-threading. We've got 8-core devices that are pretty common in the kind of mid and high end of Android now. More multi-threading is better, essentially.
Right, but then you get into power and thermal issues.
You do, but to some extent, yeah. The CPU is the dominant power consumer on the system. It's not the display, it's not the GPU, it's the CPU. So you do have to be careful with CPU power consumption.